Hello, I am actually making a video here for limits and continuity. So in my video, I'm going to go over a couple of examples with you. Hopefully you started with the video that I posted on Classroom. So if you haven't, go ahead and pause this and go back. And it's Krista King who really goes through the definition and does an example as well. We do have a definition here for how to find the limit of a multivariable function. So we're evaluating the limit as both x and y go to some values for x0, y0 there. And so if f is continuous on a region, it will be continuous at every point in that region R. And so this is the same definition that we've always used for limits and continuity. We just are looking at some examples in this video of how to evaluate that on a multivariable function. So our first example, we're going to evaluate the limit as our xy point goes to 0, 0 here of this multivariable function. And so what we want to do is we're going to do a couple of tests for this one. So the first test we are going to do is along the x-axis. Now, there will be a couple different things you may be asked specifically to test along an axis or a line or something like that, or you can just use some of the ones that we've used in the examples here. So we are going to test along the x-axis, and we're going to test it along the line y equals x. And we're going to see if the limits approach the same value. So on the x-axis, the limit as our xy point. Now, keep in mind, if we're going along the x-axis here, that y is equal to 0. And so we're basically going to test the limit of our ordered pair x comma 0 as it heads towards 0, 0, since y is already equal to 0. And so we're going to basically just be looking at x then at that point, because we know that y will be equal to 0. So if I have my function x squared minus y squared over x squared plus y squared, and that whole quantity is squared, then really I am just looking at my x values, because here this y term is going to go to 0, that y term is going to go to 0. And so I'm looking at the function x squared over x squared quantity squared. And so that limit will be 1 based off of the fact that y will be equal to 0 along the x-axis. So again, this is the first test. This is the x-axis right here. So the second test we're going to do, make sure it approaches the same value here, is y equals x. That will be our second. And so for that, if I'm approaching that limit for my ordered pair, then really what I'm looking at is that y and x are going to be the same value. So if x is some value, y will be that same value. So we're looking at what happens as that approaches 0, 0. And again, of my function x squared minus y squared over x squared plus y squared, quantity squared. And so if I have the case that my x and y are the same value here, then really this is also equal to x. And this right here is also equal to x. So where I have the numerator concerned, it's going to be x squared minus x squared essentially, which gives me 0. In the denominator, I have x squared plus x squared, which is going to give me 2x squared. And that quantity is squared, but this is equal to 0 overall as a limit. And so what happens here is that because my limits do not match, that my limit does not exist. The same rule applies as single variable calculus, that if I test two different limits and they don't match, the limit does not exist. So this would happen because we have some sort of a non-removable discontinuity. All right. And so again, just keeping in mind that happens if I get an evaluation here along one line that's different from the other line, that the limit would not exist. Okay, so let's do another example, different function over here. We're going to also just keep to approaching 0, 0 there and just change out our function. And again, keeping in mind too, if I were just to plug in 0, 0, and the same thing applies for this last example, if I just plugged in 0, 0 here, we would get 0 over 0, which is why we're doing these different tests. So if that is not the case, if you have a function where this doesn't happen right here, then you can evaluate this as a normal limit where you're plugging in the x and the y and kind of seeing what values you get there. You could still test along some different lines as well. But it's really because for each of these examples that we're looking at, that if I plug in 0, 0 right here, I am getting L'Hopital basically, 0 over 0. And this is why I'm doing these tests. So we're going to do the same two tests for this one. We're going to go ahead and test it along the x-axis first on this one. And then we are going to test it along the line y equals x as well. So testing along the x-axis again, the limit as x comma 0 heads to 0, 0 of my function here would give me 0 right here in the numerator. And then, of course, this term will go away. But if I end up getting 0 in the numerator and then what looks like to be just x squared in the denominator, my limit here is 0. So I'm going to test if something different is happening along y equals x. So we test the limit as x comma x, if they're both the same value, approaches 0, 0. Okay, so now what I'm getting is that this y will go to x, this y will also go to x. So we're going to be combining some like terms here. Multiplying this x squared by this x right here gives me 5x cubed. And then adding these like terms down here, x squared plus x squared gives me 2x squared. You can do a little simplifying here, and it looks like I get 5 halves x, which is, again, I'm looking at an x value going towards 0. And so evaluating 0 right there would give me 0. I didn't have to do that for anything else because everything else just simplified where I didn't actually have to plug in my x value at all. So now here I plug in that x value of 0 that we're headed towards, and I see that the limits themselves do match. And so this means that I do have a discontinuity at this limit as I'm approaching 0, 0. I do have a discontinuity because this happened up here where I got 0 over 0 by just evaluating it directly evaluating it. And so when we do these tests, we do have discontinuities because the very nature of the fact that we have to do this test. But in this case, this discontinuity is removable. So I'd have something like a hole in my graph or something like that where it's continuous everywhere else along the graph. But maybe I just have some type of hole in the graph. And we can look in the book, there are some good illustrations of a removable versus non-removable discontinuity and what that would look like on our three-dimensional graphs. Let me know if you have any questions, and I hope you have a great day.